Okay, so today we have Joao, who was at CMU a few years ago. He'll be talking about a series of work on noisy versus bounded leakage. So take it away.
Oh, sorry. Yeah, thanks. I got this message on my screen. Yeah, thanks, Wang, for the introduction. Right. So okay. So I'm going to tell you about some kind of relationship between noisy leakage and bounded leakage. I'll get to that in more detail in a bit. Okay. So this is based on joint work with a lot of very smart and really cool people. Okay. So Gianluca, who was a PhD student at Sapienza, is now a postdoc at ETH. Antonio Faonio is at Eurocom, Maciej Obremski at National University of Singapore, Lance Roy from Aarhus, Maciej Skurski, who at the time was in Luxembourg, FX Standard from UC Louvain, and Mark Simkin, who's in Aarhus, and Daniele Venturi from Sapienza. Okay, so this is actually two works. It's a work that came out in Eurocrypt 2021, and more recent work that's kind of a refinement of the first work, okay, that came out recently at Crypto 2024. And so most of the presentation, or basically the results I'm going to present, are actually from the Crypto 2024 paper, but this whole direction is from these two papers together. All right. So yeah, so I mean, the talk is going to be about side channel attacks. And so what are side channel attacks? So, if you implement a cryptographic scheme, you're going to implement it in the real world. It's going to be sitting in like hardware, right? And of course, there may be physical hardware properties that allow you to carry out like attacks that are just not taken into account in your theoretical model of security, right? So for example, you have here a system, it has many components. There's maybe a secret component like a secret key, and there's an adversary that can actually, again, use real world things like, it sees the system, computes, so it interacts with the system, can use some physical machine to kind of measure things like power consumption over time, or the emission of electromagnetic radiation, or even time elapsed until you get certain outputs, so timing attacks. And at a very abstract level, this means that the adversary learned some side information or some leakage, call it f of k, about your, say, secret key k. Okay. So this is the setting in which we're working, and leakage-resilient cryptography is really just the field or the subfield of cryptography where we're interested in designing or in studying cryptographic schemes that still remain secure even when the adversary is able to mount a wide class of side channel attacks. Okay, you want this class of side channel attacks to be as general as possible. Okay, by the way, feel free to interrupt me if you have any questions, of course. All right, so first thing I want to say is that side channel attacks can be very cheap. Okay, there was this very cool invited talk by Paul Cocker at Crypto 2016, where he's telling the story about, while like in the 90s, where, he went out, he bought like the cheapest possible tools he could get, and he actually used those to break like a lot of cryptographic schemes that were out in the wild. Okay, just using, again, properties from like physical hardware in which these schemes actually live. All right. So, okay, so in theoretical cryptography, we usually study leakage-resilient cryptography in what we call the bounded leakage model. Okay, so this is the model where you have a key that's like n bits long. You get some leakage, and your leakage is going to be an arbitrary function of your key, and this function will have an L bits long output, where L is some threshold that should be, you should think of it as being significantly smaller than the size of the key. Because of course, I mean, if L equals n, then there's no hope for security. So think of L as like a fraction of n. Okay? So for example, I mean, a reasonable example is to think like your key is like 512 bits long, and you are able to learn any function of your key that has a 256-bit output. Okay, so this would be like you learn half of the key essentially. Okay? And this model is very well studied. Okay, we know many cryptographic schemes with great bounded leakage resilience properties. Okay, for many different advanced crypto tasks. So for example, we have schemes that if say I tell you 99% of the key, then these schemes will still remain secure. Okay. Right. So I think we should also, look at the real world and ask, we have this model that we study in practice, that we study in theory, that's like the bounded leakage model. Does this correspond to what happens in the real world? And the answer is that it doesn't really, because in the real world, the leakage that is produced by side channel attacks is not bounded. Okay, so you think that you're applying some oscilloscope to your the computation that's happening on your system, and these will produce, say, even if your key is like 512 bits long, these will produce, say, megabytes of data. Okay, say hundreds of megabytes. So of course, if you think about this in terms of bounded leakage, it doesn't really make sense, because in terms of bounded leakage, this would reveal the key. But what happens in practice is that this is a long string that carries some information about the key, but it's also quite noisy. Okay, so I guess the next question is, how do we model this noise, right? And there are several different measures of noise out there. So, for example, one measure is you can bound the mean entropy you lose when you learn the leakage. Okay, so basically what's happening is that the average conditional mean entropy of your key when you reveal the leakage should not be much smaller than the original mean entropy of your key. Okay, and L here controls like this, it's like a loss parameter. You can also think about bounding the statistical distance between the joint distribution, okay, of the key and the leakage, and the product distribution of the key and the leakage. Okay, this is pretty much the same, okay, by Pinsker's inequality. This is pretty much the same as bounding the mutual information, okay, between the key and the leakage f of k. Right? Okay, so we have these models, and I guess the question that really motivated this line of work is the following, right? So we have, on the one hand, in theory, we know a lot of things about schemes that are resilient to bounded leakage. Okay. On the other hand, in the real world, we have leakage attacks that are noisy. They're not bounded. Okay. So what we'd like to have is to have some sort of generic result that would allow us to say that resilience to bounded leakage implies some sort of non-trivial and useful leakage resilience to real world side channel attacks, so noisy, unbounded side channel attacks. Okay. So, of course, this is an open-ended question, okay, because of course it depends on the model for the noise that you choose. So what we like to do, and this was really the main aim of these two works, is that we want to identify a noisy leakage model, okay, that first of all, okay, it really does have this, it satisfies this property, okay, so in some sense, it can be simulated by bounded leakage with useful parameters, which would mean that if you have a scheme that is resilient to, say, 50% bounded leakage, okay, then this would mean that this scheme is automatically also resilient to your model of noisy leakage. Okay, so that's the first thing. And of course, we also like this model to be useful to practitioners. Okay, this model should capture real world side channel attacks with good parameters. Okay, and I won't tell you right now what are good parameters. I think we'll get there organically. Okay, as we go along. But so how does this, how would you verify this in the real world? Okay, so there's a practitioner that is carrying out, maybe is testing a certain concrete attack on a specific device. Okay, and sometimes the noise characteristics actually depend on the specific device that you're working with. Okay, so you could say test your device to kind of get a feel, actually get an estimate for the leakage distribution. Okay, then ideally there will be a way for you to check, for the practitioner to check if the leakage falls into the noisy leakage model that we're proposing. Okay, and hopefully this should often be the case. And then what would happen is you could then automatically say something about your system just by knowing that it's resilient to bounded leakage. Okay, and usually also I want to mention that proofs in the bounded leakage model are usually much simpler and cleaner than against like noisy leakage. Okay, so that's also one perk here. All right. So I mentioned this about simulating, you know, that our noisy leakage model should be like effectively simulated by bounded leakage. And what do we mean by this? So we're going to take a very general perspective. So forget, you know, particular systems or like secret keys or whatever. Okay, there's a secret random variable X. Okay, and in the ideal world, what we do is like we learn some randomized leakage Z. Okay, so some randomized function of X. And that's the ideal world. That's like the noisy leakage function that we would like to simulate. Okay, so in the real world, what we're allowed to do is that there's a simulator that depends on this leakage function F. Okay, what the simulator can do. So again, we're trying to simulate the noisy leakage using bounded leakage. Okay, so the simulator gets to ask one bounded leakage query to X. So the simulator chooses a bounded leakage function, okay, with a certain threshold, gets back the output of that leakage function, and then can like do things on top of it to output some estimate Z tilde for the true leakage, okay? And what we require is that, or the way we define simulation is that these two experiments, okay, they should be close in statistical distance, okay? So epsilon here is the simulation error, and L would be the threshold of the bounded leakage that gets that achieves the simulation error. Okay, does it make sense?
So I guess you're going from the idea is you want to show that like noisy leakage is not much worse than bounded leakage. So you give simulator, you give a simulator bounded leakage and you tell it to simulate the noisy leakage.
Yeah, so you tell like actually, so I get the way I see is like, so the simulator knows the noisy leakage function it has to simulate, right? And then the simulator itself, like it say samples the bounded leakage function. Okay, so like it's gonna define the bounded leakage function. It can like get the output of that bounded leakage function from X, and then uses it to create the simulated leakage.
Yeah.
Okay, and we require that these two experiments are close in statistical distance, even when I tell you what X is. Okay.
Yeah.
And essentially, if I have this property, so if I have, say, if epsilon is very small, and I have this simulation, such a simulation statement for a class of, say, noisy leakages, then I know that any scheme that will be resilient to bounded leakage, okay, will be automatically resilient to that class of noisy leakages as well. And you're going to pay this epsilon, this extra epsilon term in the error. All right. So let me say that, you know, this kind of problem is like not new. Okay. So this kind of dichotomy has been studied in the past with respect to like leakage from circuits. Okay. So there's this work by Ishai, Sahai, and Wagner from Crypto 2003, where they wanted to protect circuits, okay, against wire probing adversaries, okay? And I'm going to focus on a specific model. It's not the model they originally focused on, but it's kind of equivalent, okay? Which is a model, it's called the random probing model, okay? There's a parameter P. And in this model, let's say you have a circuit, it has a bunch of wires, and you know, there's an adversary that's interacting with the circuit. Maybe, you know, I guess in the simplest setting, imagine that the adversary doesn't know the inputs, okay, to the circuit, doesn't know the outputs, okay? But he's trying to infer something about the inputs and the outputs from leakages from each circuit wire, okay? And the model for the leakages is that basically the adversary learns a random p fraction of the value of the circuit wire, of the values in the circuit wires. Okay, so for each circuit wire with probability p, it's going to learn the value that's inside. Otherwise, it learns nothing from that wire. And they have very elegant compilers for this model, where basically, you give me any circuit and I compile it to an equivalent circuit that is resilient to this type of probing leakage. Okay, so what's the issue, right? The issue is that in practice, again, the leakage is not really, the probing model doesn't really correspond to the real world. Okay, so actually what happens in the real world, you could think, is that from each wire, the adversary is actually going to learn a noisy function of the wire value. Okay, and so now the question is, okay, we know how to protect circuits against probing leakage, but then how do we protect circuits against noisy leakage from each wire? And there was some early work on this where they actually showed with some different arguments and using stronger assumptions like leak-free components and other things that the actual schemes from Ishai, Sai, and Wagner, they were actually still secure against some type of noisy leakage. Okay. But then later on, there was a result that I really, it's a result that I really like from a conceptual standpoint. Okay, it's by Duke, Timbowski. It's a series of work by Duke, Timbowski, Faust, and Stander, where basically the key result is the following. Okay, it's like if I have a uniformly random secret X, okay, then I can actually perfectly simulate any noisy leakage function that satisfies this condition here. So the condition should be that the statistical distance between the joint distribution of the secret and the leakage and the product distribution of the secret and the leakage, they should be at statistical distance at most delta, okay? And I can perfectly simulate this using one query of random probing leakage with parameter p being equal to delta times the size of the support of X, okay? Why do I like this result? Okay, so if we have this result, then this follows very readily from the original result of Ishai, Sai, and Wagner, because this immediately implies that any circuit that is resilient to p random probing leakage will also be automatically resilient to what we can call delta ST noisy leakage. Okay, so noisy leakage that has like bounded statistical distance from the product distribution. Okay. And by the way, this model, I mean, practitioners like this model. Okay, so you can imagine that, like in practice, what happens is that there's noise that you can yourself add to your physical implementation, and you can add the noise so that your leakage distribution will satisfy this condition. Okay.
Is this like used in practice anywhere?
Yes. So originally, you can think of it like this. Okay, so the way you protect circuits against wire probing adversaries, you at a high level, but it's not much more complicated than this. It's just say you take a wire from your circuit. Okay, it carries a certain value, so you secret share it. Yeah. Okay, you do like active secret sharing, which means that even if I learn like a certain fraction of those wire values, right, then I won't know anything about the actual original wire value that's being sent to those masked circuit wires. Okay. Yeah. And this is used in practice. Like people do this circuit masking things in practice, but they didn't have a proof of security, right? They had proofs of security for the random probing model. Okay. But in practice, they wanted proofs of security against like some sort of noisy leakage. Okay. And this kind of simulation result from these guys tells you that, if you're resilient to random probing leakage, it tells you exactly how resilient you are to a certain class of noisy leakage. Okay, it's measured by statistical distance.
Like if you could cite like a particular place where like somebody uses like additively secret shared circuits, like you described.
I can tell you like hundreds of papers. I can send you. Yeah. I mean, do you want me to like show you now or like?
No, it's fine.
Yeah.
I was just
Yeah.
like a good example, like Google uses it to do their.
I see. I think it's a bit different than just Google using it to do something, but definitely, circuits that are like this. I mean, I'm of course like, okay, I'm a theoretician, right? So take all of this with a grain of salt. But I think if you just search online for like circuit masking, okay, or like Boolean masking, that's what some people call it, like this additive secret sharing. Okay, you're gonna find a lot of hits on people studying these implementations.
Sounds fun. Thanks.
Yeah, no worries.
Any NIST standards also come with these like masking implementation.
Can you repeat that? I didn't quite hear the first part.
Yeah, I think like when NIST standardizes a scheme, does it also come with a masking implementation?
I know. I mean, I think I'm not sure. So I think I think they make an effort for them to make the code like constant time so that you don't do like timing attacks and stuff. But I'm not sure if they do like mask. Maybe they do. I don't know.
Yeah. Do you know of like what Matan said, maybe like a situation in practice where you absolutely need to have this masking instead of just a regular implementation?
I mean, I think people use like masked implementations of like AES.
Mm-hmm.
Yeah. I cannot tell you more than this because I don't know. It's like that's above my pay grade.
Yeah. Okay, cool.
Yeah. No. All right. Yeah. Okay. So there was this other problem, right? So like just kind of circling back, there was this other problem, like, it's kind of related on leakage from circuits, and there was this nice conceptual result, that kind of very nicely, connected everything together, and now we have a very nice way of translating random probing leakage security to security against noisy leakages. Okay, and of course, I think proofs in the probing model are usually very clean, or much cleaner than for noisy functions. All right. So, okay, but what was the problem we cared about? Well, the problem we cared about was like simulating noisy leakage using bounded leakage. That's a bit different than simulating noisy leakage with probing leakage. Okay. So I guess we talked about this, this ST noisy model. Okay, so measuring noise with a statistical distance. Okay. And we know that it's perfectly simulatable by a random probing leakage where these parameters are related, right? So P for random probing is delta times the support size for your secret. Can we have an analogous statement for bounded leakage, okay, instead of just random probing leakage? So that's the first question we want to answer. And so let's look at an example. Okay, let's actually look at the example where X is uniform over 0, 1 to the n, so it's uniformly random n-bit string, and Z, the leakage, will be delta random probing leakage from X. Okay, so in other words, Z is with probability delta, Z will equal X. Otherwise, Z is like bottom. Okay, it's a special symbol that doesn't reveal anything about X. So some observations. Well, first of all, observation that Z is delta SC noisy leakage from X. Okay, so it's in the model. We can trivially simulate Z from 0 bits of bounded leakage with simulation error delta. Okay, like literally just output bottom. Okay, does that make sense?
Yeah.
Yeah. Okay. But it's also not that hard to see that actually we cannot simulate Z with error below delta over 2, even if we have like n-1 bits of bounded leakage. Okay, just imagine that we leak the first n-1 bits of X. Okay, I know that with probability delta, I need to tell you X, right? Because otherwise you're going to realize I'm lying. But I don't know the last bit of X, so I have to guess, and I'm going to be wrong with probability half. Okay, so that's the intuition. Okay, so what's the conclusion here? Well, the conclusion that, of course, we need to come up with a different, we need to study a different noisy leakage model if we care about, say, noisy leakage versus bounded leakage. On the other hand, we're still optimistic because this counterexample, we can call it like a catastrophic leakage, okay, where with some probability delta, that's like, think of delta as not being necessarily negligible here, okay, that these don't really occur in practice. Okay, so we'd still hope that we could come up with a model that is good for simulation from bounded leakage. It's also good for capturing real world side channel attacks.
Wait, what's the leakage here? Like,
sorry, can you repeat that?
So what's the noisy leakage here?
So the noisy leakage so Z is the noisy leakage, and Z is delta random probing leakage from X. So in other words, it's like Z tells you X with probability delta, and otherwise tells you nothing with probability 1 minus delta. That's your noisy leakage, okay? It's noisy in the sense that it fits inside this delta ST noisy model, okay? Yeah, but what I'm saying, the point I wanted to also put forward is that these types of leakages, they don't occur in practice, okay? So they're not a priori, at least, a barrier towards finding a good noisy leakage model that can be simulated from bounded leakage.
That makes sense. That's good.
Yeah. Okay. So where do we go from here? And I think it's kind of natural to try to think, we looked at statistical distance, it didn't really work. Like, how can we extend statistical distance? Okay, there are these things called hockey stick divergences. Okay, they really just generalize statistical distance. One way to define them is to say, I have this T hockey stick divergence. Okay, there's this parameter T here in red. I also going to call this SDT. Okay, and the T hockey stick divergence between two distributions, P and Q, is going to be at most delta, if and only if this condition holds. Okay, and the condition basically says that the mass that P assigns to any set S is never more than 2 to the T times the mass that Q assigns to the same set S plus some slack delta. Okay, and this should hold for all sets S. So why does this generalize the statistical distance? Well, if you set T to 0, this is literally statistical distance. Okay, this is basically saying that statistical, like that SD0 of P and Q being at most delta is the same thing as saying that the statistical distance between P and Q is at most delta. But now we have this extra parameter, right? So we can play around with T. Okay. So some useful properties so the first property you kind of inherited from statistical distance. Okay. So there's a formula for computing in some sense the delta that you should be looking for. Okay, it's just the sum of this maximum. And you also have this property that as you increase T, then your T hockey stick divergence between the two distributions will decrease. Okay, and I think proof by picture here is very nice. So if you see here that if this blue line is your distribution P, your orange line is your distribution Q, and really what you're doing when you're computing the T hockey stick divergence is that you're really summing up only the red region. Okay. And so you see, as you increase T, the red region becomes smaller and smaller. Okay.
Why is it called hockey stick divergence?
That's a good question. It's because if you see it as an F divergence, okay, there's this thing, there's like this general notion of a divergence called an F divergence. It's actually something you can really easily Google as well. Like if you Google for F divergence, there's like great write-ups on this. And the F function that you use to get this to basically induce these divergences, it looks like a hockey stick. It's kind of like this. Like it's like flat and then it goes up.
So just the definition that you wrote down there, it should actually be like a symmetric definition, right? So
that's a good question. Yeah, that's a good point. So this divergent, like as soon as T is larger than 0, this stops being symmetric.
Oh, really?
Yes.
So the divergence of P from Q is not the same as divergence of Q from P?
Yes, that's true.
Oh.
Yeah.
Oh,
Yeah.
okay. Yeah, I guess.
So, but I mean, here, like, again, we're exploring models, right? So you could think, and we do actually do that in the paper, although I'm not going to talk about this in the talk, which is like, we have this notion. I mean, we're going to basically define our noisy leakage model in terms of like this hockey stick divergences, okay? But you can also think about defining your noisy leakage functions in terms of, the two constraints on there are two hockey stick divergences here. There's a hockey stick divergence from P to Q and from Q to P, right? You could enforce both, and then you have a symmetric definition, right?
Yeah.
Okay. And that we also explored that in the paper, but not in this talk. But that's a good point. It's not symmetric.
Okay, sure.
Yeah. All right. So, okay, so what is what we call the T delta ST noisy model? So now, beforehand there was a delta, now there's a T and a delta. So there's an extra parameter, which is good. It gives it more freedom. Okay, so basically I'd say that Z is T delta ST noisy leakage from X if the T hockey stick divergence between or from the joint distribution between secret and leakage to the product distribution between secret and leakage is at most delta. Okay, and again, same picture. Right? I just want to show you that what you see here, like what is the thing that what are the values that we really care about. So if blue is your joint distribution, if the blue line is your joint distribution and the orange line is your product distribution, you really care about the red region again, which is like everything that's above 2 to the T times the product distribution. Okay. Right. So this is our
sorry, there.
Yeah, no worries. Yeah.
There was a question in the chat, I think.
Sorry. Yeah. Go on. Do you want me yeah. Sorry.
Yes. So George asked a question. Hockey stick divergence seems pretty similar to the differential privacy definition.
Yeah. That's great. That's a great observation because it is the same thing.
Okay.
And we're gonna use that.
Mm-hmm. But
yeah.
in differential privacy, you use like E instead of 2, right?
Yes, that was okay. The 2 here is a conscious decision on our part because we're going to get cleaner results that way. We don't have like some trailing logs.
Okay.
Okay.
Yeah, George.
But that's a great observation. Yes.
Who's George? Is this George Lee? Wait, you can answer, George. No. Okay. George Lee also does differential privacy.
Yeah. Is there any other questions or?
We don't need a George, but you can keep going.
No, I think it's good.
It's good. Okay, perfect. Yeah, no, but that's a great observation, and we're definitely going to use that. Okay, and all right. So yeah, that was my next slide, basically. Okay, so this thing also shows up in differential privacy, and in fact, I mean, you can, we're defining, basically, you can define epsilon delta differential privacy is basically just saying that the T hockey stick divergence between the mechanism on X and the mechanism on X prime is at most delta for any two neighboring databases X and X prime, and the T that you take here is basically going to be epsilon, but now you need to change the 2 to the T to an E to the epsilon. Okay, so that's why you have this log E there. Okay, but the reason why we chose to do an exponent base 2 instead of E is that we'll see shortly. It does lead to cleaner theorem statements in the setting of leakage resilience. Okay. All right. So this will definitely be relevant later. Like we're going to use this connection. All right. So first result. Okay. So we have this model like T delta ST noisy leakage, and I guess the main result we prove in the paper, okay, is that it's basically a simulation statement or a simulation theorem for T delta ST noisy leakage. Okay, so it basically says, I'm just going to read what's here. We're going to try and unpack it a bit, but it says like, you give me any alpha. Okay, alpha can be whatever you want, and then the class of T delta ST noisy leakages will be delta plus alpha simulatable from T plus, log 1 over alpha bits of bounded leakage. So I think the way you should read this is that if I tell you I have a T delta SC noisy leakage function, this means that I need T bits of bounded leakage to simulate it with error delta. Okay, so the T, you should read it as number of bits of bounded leakage, delta simulation error. Okay, and again, the reason why I wanted to use 2 to the T instead of E to the T is really that then this theorem statement will not be as clean. Okay. All right. So this is our main theorem. Okay. And let me just tell you how we prove this thing. And it's basically like we're going to define a simulator, and the simulator will basically do rejection sampling. Okay. Okay, so here's what we call the rejection sampling simulator. So what does it do? Okay, it has a certain parameter L. Okay, L is going to be the number of samples we're going to use to do rejection sampling. Okay, and so you're the simulator, right? So you don't have access to X. Okay, you can only have access to X through a bounded leakage function. Okay, so what you're going to do is we're going to sample L IID samples from the marginal leakage distribution, okay, Z1 through ZL. And based on these samples, ZI, I'm going to define this bounded leakage function G of Z, okay? So this bounded leakage function basically runs rejection sampling with the ZIs, okay? So what it's going to do is like, now, keep in mind that this leakage function has access to the secret X, okay? So what it's going to do is like for I from Z1 up to ZL, it will accept ZI with some probability. And the probability is this weird thing here. It's like the minimum between 1, okay, and this other fraction, which is like the joint distribution over the product distribution times 2 to the T, okay? And you can, for people who know about, like, that are familiar with rejection sampling, you can think about this 2 to the T as a sort of density parameter. Like it tells you like how dense one distribution is in the other, okay? And what you're going to do is you're just going to output the index I of the first accepted sample. Of course, it may happen that you don't accept any sample. In that case, you just output L, okay? Now, how many bits of bounded leakage do you need to do this? Well, you need log L bits of bounded leakage, okay? So this is my function. So I give this function to my oracle, okay? I get back the output of this function on X. And so what is the output of this function? Well, if we're lucky, okay, this will be the index of the first accepted sample. And I'll just give you that the simulator will just output that corresponding sample. Okay. Does this make sense? Or was I too confusing at some point?
Yeah, actually, sorry. I mean, it's mostly my fault.
No, it's definitely my fault. Yeah, go on.
Like, so yeah, you try to build a simulator, and the simulator takes some number of like bounded leakage function bounded leakage samples. And how does it construct the noisy leakage sample? Doesn't it depend on like what the noise is? Like,
right. So again, what the simulator does is like, let's say the first thing the simulator needs to do, okay, is kind of construct the bounded leakage function that it will send to the oracle, okay. And the way it does that is that it's going to sample IID from the marginal leakage distribution, which is basically the leakage distribution without knowing X, okay? And so you get a bunch of samples, Z1, Z2 up through Z sub L, okay? And your bounded leakage function, the function that you will query the oracle with, okay, what it's going to do is it's going to use these samples, Z1 up to Z sub L, to run a rejection sampling algorithm, okay? So what it's going to do, it's going to go index by index, okay? Or ZI, from Z1 up to ZL, and it's going to accept ZI with this probability, okay? And I think, don't think too hard about, what is this probability? It's not super important right now. And if you accept at any point, you output the first index, you output the index of that first accepted sample, Okay, so that's your bounded leakage function. It's just this thing. It runs this rejection sampling algorithm and it tells you the index. Okay, so it only needs the amount of the output size for this is really just the number of bits you need to tell me the index of a sample. Okay, so it's going to be log of L roughly.
Each CI depends on the CI sample itself.
Sorry, can you repeat that?
It seems like for each index, the probability of accepting that index depends on the sample for that index, right?
Yes, that's completely right. It depends on X and it depends on ZI. Yes, that's totally right. Yeah, and that's needed.
Okay. Yeah, because I was confused for a moment about why you were able to just pick an index if it didn't depend, or why.
Yeah, no, it definitely needs. Yeah, that's a good. Yeah, good point. Yeah, it definitely needs to depend on your ZIs, right? Because otherwise, this won't work. And then I just, the simulator will just output the corresponding sample. Okay. And what's happening here is that just an observation. First observation is that, if you had the property that the T hockey stick divergence, okay, between these two distributions, so the joint distribution and the product distribution, if this was 0, okay, this is really just standard rejection sampling, okay, which means that you see we have this probability minimum of 1 and something else, so the 1 will never happen. Okay, you're not going to get the minimum, you're just going to get the second argument from that minimum all the time. Okay, and that's really just standard rejection sampling. And what we know from rejection sampling is that actually, if you condition on the fact that some sample is accepted, simulation will be perfect, like 0 error. Okay, so what is the simulation error for your simulator? Well, it's really just the probability of you rejecting every sample, okay? And in this specific, very special case, okay, the probability of rejecting a sample, given that X equals some small x, okay, is always equal to 1 minus 2 to the minus t, okay? So the simulation error will just be, the expected value of this thing, which again, it's a constant. So you just do some very simple calculations and you get that your simulation error will be at most alpha, where, alpha comes from the definition of L. Okay, so we set L on purpose to get final simulation error alpha. Okay, this is a very special case where the T hockey stick divergence is going to be 0. Okay, but this is not the case we have. Okay, we have the case where actually the T hockey stick divergence may equal some delta, and this delta may be positive. So there's a slack, and you can think of this slack as like the bad samples. Okay, where in this minimum that you're seeing on the right hand side, you would pick the 1. Okay, which means that you just accept the probability 1. Okay, and that skews things a bit. You don't get perfect sampling, and you don't get perfect simulation anymore. Okay, if you accept something, but we can quantify how far away we are. Okay, so the simulation error will still be at most the expectation of the probability of rejecting a sample, given that capital X equals small x. Okay, and we can use just, again, some fairly simple facts about this expected value to actually upper bound the simulation error by the slack delta and alpha, okay, the sum of these two terms, okay? Of course, this is a very high level description of the proof, but I would say, it's actually a fairly simple, low tech proof that's under the hood here. All right. Any questions or anything you want me to go over again, or?
Yeah, I mean, maybe I'm just like a little confused at
Mm-hmm.
like the way I anticipated, like what you're going to do is that you're going to pick like some sort of like noisy leakage model. Like maybe you learn like the key plus some like Gaussian noise or something like that, right? And then you're gonna say, okay, well, actually, if I get like 5 random bits or like half of the random bits, then like here's how I'm going to output like the key plus like random noise, but like plus like Gaussian noise. But like I
Yeah.
really understand what I'm looking at here. Like,
Okay, so you can think of it as so actually, so what you say, it makes a lot of sense. I agree that, like, you kind of you want to look at like concrete leakage models, like noisy leakage
or like
models,
I
right?
don't understand how this connects to concrete leakage models.
Okay, yeah, so we're going to get there as well. And exactly like you mentioned, like, something plus Gaussian noise, we're going to do exactly that. Okay.
Yeah.
So what we have here, think of it this way, okay? We're defining a very general, I mean, hopefully, general noisy leakage model. It's anything that satisfies these divergence bounds, okay? And of course, we want to prove a simulation theorem for as wide a class of noisy leakages as possible, okay? And to us, this is like as far as you can push the rejection sampling algorithm. Okay, so the rejection sampling algorithm will work for any noisy leakage function that has this bound on the T hockey stick divergence. Okay, so this is a very abstract general result. Okay, so this is the first step. It's like we have a noisy leakage model. It's general. We know how it is simulated by bounded leakage. Second step is, and that's what we'll discuss after, is how well does this model that we just defined, this abstract model, capture, say, other noisy leakage models that already exist, and in particular, concrete leakage models that practitioners like. Okay, like, for example, things like revealing parts of the key plus Gaussian noise.
Okay.
Does it make more sense now?
Yeah, okay, so maybe I'm trying to like understand that makes a little bit more sense. So I'm trying to understand, you take L samples from the bounded leakage, and the idea is then you just make some number of samples from the noisy leakage, and then you accept like the sample from the noisy leakage
So the L samples are not from the bounded leakage, they are from the so Z is the noisy leakage, okay? The samples that you generate are from the marginal distribution of the leakage. So it's like, the leakage depends on X, right? But there's X and Z are correlated, okay? But, Z has a marginal distribution.
Yeah.
Okay, so you sample from that marginal distribution, which is like, you don't know X, so you cannot do anything else, okay? You sample from the marginal distribution, okay, of the noisy leakage Z, okay? And then you use this to do rejection sampling inside a bounded leakage function. Sorry.
How do you know the joint distribution of X and Z? Because you are simulating you are using bounded leakage function to a bounded leakage to simulate a noisy leakage, but you need to know the probability of like P.
Yes, that's a very good point. So right. So what am I guess, silently assuming here? Okay. So and this is fine. I mean, so and this coincides with the simulation notion I had before. So the simulator knows the distribution of the secret. Okay, it's usually like uniformly random. Okay, it knows the leakage distribution. Okay, and so you can compute, like, of course, you need to know these probabilities to compute these terms on the right-hand side.
Oh,
right?
Okay. So I know how to compute it, but I cannot directly sample it.
Yeah, I mean, it's like, the distribution of something, but you don't know what it is, right? Those are two different things.
Oh,
You could think like this makes sense in practice, because again, like you could think, first of all, like, maybe the secret is the key, right? The key is uniformly random, so that's fine. And then you can, from playing around with the device, you can estimate the leakage distribution for values of the key that you set. So you actually learn the joint distribution. Of course, when you try to attack some other device or something else, you don't know the key, right? But you do know the distribution that it follows, right? You know the distribution that the leakage follows.
Okay. Thank you.
Yeah, no worries. All right, so this is kind of the skeleton, okay, like kind of the high level thing here. And I think, I mean, you guys are asking very, very nice questions, okay? So, and this was like what I was getting to, which is, we have this simulation theorem. It tells you, if something is T delta ST noisy leakage, then actually we can simulate it with boundary leakage with some parameters. We haven't discussed like how reasonable the parameters are, okay? And the way we do this, the way we're going to discuss it is like, we need to see how our model captures, like, first of all, other noisy leakage models and concrete, like what kind of results does it give for very concrete noisy leakage functions that people actually care about in practice, okay? So first thing, okay, I just want to say, it does capture other theoretical and concrete noisy leakage models with good parameters, okay? Actually here, I think it would be very interesting to actually do a more in-depth exploration of this, okay? We've done something, but it's not, I wouldn't call it like a complete exploration, okay? So let me say, first example is that, if you want to, there are all these models of like mean entropy based leakage models where you, what you do is you only allow leakage functions that do not drop the mean entropy of your secret by a lot, okay? And there's this notion of a noisy leakage function, which being like any function that drops the mean entropy of a uniform distribution on n bits by at most L bits, okay? So the average conditional mean entropy of the uniform distribution, given the leakage, okay, on this uniform distribution, will be at least n minus L. So this is just one example of one particular model using mean entropy, okay? And actually, you can prove this is not very hard either, that we can place this whole model inside our T delta ST noisy leakage model, okay? So every L noisy leakage function f, okay, if z equals f of x, then the corresponding leakage z will be T delta ST noisy, where, T is L plus eta, where eta is some free parameter, and the error, like the delta slack, will be 2 to the minus eta, okay? What this means is that you get for free a simulation theorem for this mean entropy based leakage model, okay? I won't bother you too much with the parameters. I'll just tell you that this is pretty much optimal, okay? So you get like optimal simulation theorems for this, okay? So that's, I guess, one of the reasons why this model seems reasonable and useful is that it does seem to capture other noisy models that people have studied before, okay? And besides that, okay, I really think it's important to actually look at how it captures models that practitioners use in practice, okay? And practitioners like additive noise models. So usually they care about models where the leakage z is going to be some deterministic function of x plus some noise, okay? And this noise is independent of x. And a very popular instantiation is like, x is really an n-bit string. The deterministic function of x is just the Hamming weight of x. And n will be just a centered Gaussian with some variance sigma squared. Okay. So this is the model, like we want to try to kind of see like how well, like with what kind of parameters can we actually place this model inside our more general noisy leakage model, okay? So and then we want to, why do we want to do this? Well, because we want to say, useful things about how to simulate this concrete model using bounded leakage, right? Because if we had something like this, we could say, if I have a certain cryptographic scheme that's resilient to this amount of bounded leakage, then I know it's going to be resilient to this specific type of noisy leakage that is a good model of real world side channel attacks. Okay, and I want to make this translation. Okay, so what do we know about this particular model that we chose here? Well, it's trivially simulatable from log n bits of bounded leakage. Just tell me the Hamming weight. Okay, but I guess the question is, if I increase the noise, so as a function of the noise that I add, right, this discussion with the variance, how much better can we do than using log n bits of bounded leakage to simulate this leakage model? Okay. By the way, let me just show you like how does this leakage model, how do these concrete leakages like behave? Well, on top, you have basically the leakage with a very high signal to noise ratio. This is basically the setting where your noise is like it's not very noisy. Okay, so you have the bump, so you can clearly see that the leakage is really telling you the whole Hamming weight. Okay, if we increase the noise, then the signal to noise ratio decreases. Okay, and you start seeing there are a bit more fluctuations. And if you increase the signal to noise, so if you increase the noise even more, so the signal to noise ratio decreases, you start seeing more of a smooth curve. Okay, so this is telling you less information about the actual Hamming weight of your secret. All right, so here's a bunch of plots. Okay, what do these plots have to tell us? Okay, so again, so this is Hamming weight plus Gaussian noise. I have here, so what is the signal to noise ratio? This is really just the ratio between the variances of the two distributions, okay? The deterministic function of x, okay? And the noise, okay, n. Again, just to remind you that because of our simulation theorem for T delta SC noisy leakage, okay, you should think of T as the amount of bounded leakage that you need, okay? And delta, the simulation error, okay, that you're aiming for, okay? And let me just tell you what to me is the main takeaway from these plots, okay, is that let's say we're trying to get simulation error that's roughly 2 to the minus 128, okay? If we don't assume any form of bounded leakage resilience, okay, that's the plot with the T equals 0 plot. So it's the one on the bottom right, okay. You need to add noise into your physical implementation, okay, to reach a signal to noise ratio that's like 2 to the minus 128. So it's basically comparable to simulation error. Okay, this is not realistic. We cannot do this. Okay. However, if we say that, okay, actually the cryptographic scheme we're working with actually resists, say, log n over 2 bits of bounded leakage, okay, so this is half of the trivial bound, okay, then actually, so this will be the plot on the top right, okay. Then in this case, we only need to add enough noise to get the signal to noise ratio to be roughly 2 to the minus 10, okay. So this is a big improvement, okay, over the version without bounded leakage resilience. And reaching these signal to noise ratios also of around 2 to the minus 10, this is actually realistic. Like people can do this in practice with real world implementations, okay? Any questions about this? Yeah. Okay. So I guess Matan, was this like what you were going for like initially? Was that like something of this form?
I think I was more so looking to like, I mean, like I think maybe it would be, I was looking to like understand what the simulator like does concretely, like give these things, and I think like the description maybe in like the generality and like the Indian food, which is like subduing my brain abilities. Like I have lost what the simulator kind of actually does, like to simulate. Like I understood that yeah, I actually probably still couldn't tell you very well what it actually does to simulate in a concrete case. Like I thought something kind of abstract, and maybe because of that, it kind of went a little over my head.
Sorry. No, yeah, I think
Like I understand, like
mhm.
I think you painted well, like the overall like aims of your work, and like some I have some understanding of like how successful they were. It seemed
Yeah. So I mean, if you're interested, I mean, of course, I'll be happy to take this offline and we can chat. If you're curious to learn more.
Wrap up soon.
But you can just think that like what rejection sampling is doing is so there's like some sort of let me see how I can put it. There's what the bounds on the T hockey stick divergence is telling you is kind of like there's a that okay, I think the technical term for this is like that one of the distributions is like dense in the other distribution. Okay, so what you have is that one of the distributions is never or one of the mass that you assign to anything is never much larger in one distribution than the other. Okay.
Yeah.
And rejection sampling, okay, is basically a general tool. It goes much beyond this. Like it's a general statistical tool that allows you to turn such a statement into saying that, okay, if I have this guarantee between these two distributions P and Q, like this density guarantee, okay, then I can actually simulate, like very efficiently, okay, simulate, say, samples from P, okay, using only kind of samples like based on IID samples from Q. Okay, it's like this thing where I want to use Q to sample from P. It's like there's some sort of mismatched estimate, like sampling.
Okay, I think now it makes more sense. Yeah.
Okay.
See what about, yeah, that makes sense.
Yeah. Okay. No, thanks. Okay. So right. So this is kind of like just to kind of recap. Okay. So what did we do? So we had this T delta SE noisy leakage model. It has some simulation theorem from bounded leakage. Okay. Why is it useful? Well, it's here in this slide. Okay. If you have this very concrete model like Hamming weight plus Gaussian noise, you can use our general simulation theorem to get some nice guarantees. Like you can think of this as like a trade-off, right? As you increase the amount of bounded leakage that you allow, the signal to noise ratio that you have to achieve is much, much more reasonable. Okay, there's a very nice trade-off here. Let me just kind of wrap things up by changing. So we've been talking about simulation for a while. So let me talk about something else. Let me talk about composition of leakages. Okay, which is also something very relevant in practice. Okay, because in practice you don't really just get, say, one leakage from the secret. It's like you have a system that's like computing something, and you interact with it as it computes, and you're going to get multiple leakages. Okay, from your secret X. So we're going to make the simplifying assumption here that these leakages are conditionally dependent given X, which is an actually reasonable assumption because if you think about the additive noise model, okay, this is definitely true because your additive noise is always independent of your secret, okay? And I guess the question we're trying to answer here is it's again something that tells us like, at least reassures us that our model is reasonable is, if we know that each leakage ZI is actually TI delta I ST noisy leakage from X, what can we say about, the joint leakage, this tuple of leakages, okay? And it turns out that we can actually say quite a lot. So the answer is that Z is T prime delta prime GST noisy, and I'll tell you what the G means is not a big deal. okay, where T prime is just summing the Ti's, okay, delta prime is just summing the delta i's. And the G just means that we're changing the definition slightly. And so beforehand, for ST noisy leakage, we required that the T hockey stick divergence between the joint distribution and product distribution of, PX and PZ, okay, would be small. So it would be at most delta. In this case, we only require that there exists a distribution Q, which may be different from the marginal distribution of the leakage, such that that makes this divergence small, okay? So it's a wider class of noisy leakage functions, okay? Fortunately, by the way, let me just say that the proof for this, it's really just, and this is where we use the connection to differential privacy, is that, we do have composition for differential privacy, okay? You can use a standard composition. If you just trace the proof, you apply it here, you get composition for our leakage model. So it's very simple. And let me just say that, fortunately, the things we've seen before, they actually apply to this more general model of noisy leakages, okay? The G here stands for generalized, okay? It's not super important. And people that know differential privacy may be asking, if we could prove, say, standard composition, okay, there's this thing in differential privacy called advanced composition, which is like, it allows you to compose differentially private mechanisms, but like pay less penalty as you compose these things. And we can also do advanced composition here, okay? It has the same limitations that advanced composition has for differential privacy. And in our case, okay, in the case of leakage resilience, this actually makes advanced composition, or at least the advanced composition results that we are actually able to obtain, not that interesting because they were like in a regime that's not practically relevant. So it's a regime where T is pretty small, okay? All right, so this pretty much wraps it up. Let me just recall what we did. Okay, so first of all, there's this whole theory of leakage resilience that's beautiful, okay, but it focuses on the bounded leakage model. It's the proofs are very clean, they're very elegant. On the other hand, the real world is a bit messy, okay? So real world side channel attacks, they do produce noisy leakage that is unbounded. We have this model, T delta SE noisy leakage, okay? And we have these results, like our main results, saying that basically, if we're resilient to T-bounded leakage, okay, then we're essentially delta resilient to T delta SE noisy leakage. And we can use this result to actually obtain automatically just simulation theorems for existing noisy leakage models, including leakage models that practitioners care about just automatically. Finally, we have this thing that, T delta SE noisy leakages, they compose very nicely. And this is very good for arguing about a system where you're leaking multiple times, okay? You can just go back to the original SE noisy leakage model. All right, so this is all from me. Yeah, thanks for listening and for the great questions.